Hello friends, welcome to Mu Lessons. Today our topic is about measuring instruments. In our daily life we come across the terms like power, energy, voltage, current. So there are several devices, maybe analog or digital, to measure these things. So we will talk about some of these kinds. The first thing is the basic thing. What is measuring instrument? It is a device used for comparing the unknown quantity with the unit of measurement of standard quantity. Means we are given with standard quantity and we use this device to compare with the unknown quantity with the standard quantity, and that calculations is done by the measuring instrument. How can you classify these instruments? These instruments may be divided into two types, that is absolute instruments and secondary instruments. These are basically of further divisions can be like the absolute instruments give the quantity to be measured in terms of instrument constant and its deflection. The amount the spring or the wire deflects is given by the absolute instruments. It is the quantity measured in terms of the instrument constant. It purely depends upon the present instrument. But in case of secondary instruments, the deflection gives the magnitude of the electrical quantity. It has been compared with another standard instrument before putting into use. That is known as the secondary instruments. Here you can see the pictures like this is a temperature reading instrument, that is a pressure reading instrument. Electrical measuring instruments may also be classified on the terms of the quantity, the kind of current and the principal operation. These are the basic divisions of instruments. Suppose we consider classification of secondary instruments. This can be of three types like indicating instruments, recording instruments and indicating instruments. So first of all we'll talk about the indicating instruments. In this case we are having a screen, several units of divisions, and the movement of the pointer indicates the measurement. It indicates the magnitude of the electrical quantity at the time when it is being measured. The indications are given by the pointer moving over a graduated dial, and this movement of the pointers through the dial gives the measurement. It is just like our wristwatch. The minute hand or the hour hand moving on the dial gives us the time. Simply, it is a type of indicating instrument. Now second is the digital type, that is the recording instrument. These instruments keep continuous record of the variations of the magnitude of the electrical quantity to be observed over a definite period of time. Hence these are called the digital instruments, or they are most usually used for recording instruments like a camera, a mobile phone. This is the most important thing, that is the indicating instrument. These instruments measure total amount of either quantity of electricity or electrical energy supplied over a period of time. Means the instruments which we use for measuring our power in our house are the indicating instruments. They measure the total power for a certain amount of time and hence known as electrical instruments. Some of the essentials of indicating instruments as defined above. Indicating instruments are those which indicate the value of the quantity on the dial. Such instrument consists of a pointer which moves on a scale, and where the pointer moves on the scale, that point is to be measured. And the moving system is the most important part in this case. The moving system has three types of torque, that is a deflecting torque, controlling torque and the damping torque. These three things are basic things. The deflecting torque is otherwise known as the operating torque. Means the pointer goes away on the scale. This is the deflecting torque. Controlling torque is the restoring torque. The torque responsible to bring the pointer to its original position is the restoring torque. And similar is the damping torque. First, briefly we will know about deflecting torque. This torque is produced by making one of the magnetic, heating, chemical, electrostatic or electromagnetic induction effect. But in most of the cases it is either magnetic or electromagnetic induction effect of current or voltages, and this causes the movement of the system of the instrument to move its zero position. The method of producing this torque depends upon the type of the instrument. Next is the controlling torque or the restoring torque. The magnitude of the moving system would be somewhat indefinite under the influence of the deflecting torque. Unless the controlling torque exists to oppose the deflecting torque, it increases with increase in deflection of the moving system. Under the influence of this restoring torque, the pointer will return to its original position. This controlling torque, or better known as restoring torque, is responsible for bringing the pointer to the original position so that we can measure again on the same dial. Without the controlling torque, the pointer will swing at its maximum position and will never return to its original position, and this is called error. Controlling torque can be produced either by a spring or gravity control, but the best method is the spring control. So this is a picture shown of the spring control. Here you can find a pivot to which a rod is attached, and a scale that is acts as a pointer, and here the point A and B are used as the control springs. When the pointer is deflected, one spring unwinds itself while the other is twisted. This twist in the spring produces a restoring torque, which is proportional to the angle of deflection in the moving system. This is a very important step. In this case, the controlling torque Tc is directly proportional to theta, and this theta directly proportional to the current flowing through the circuit. This current, the magnitude of current flowing through it measures the angle of deflection, which is equal to the controlling torque, and this deflecting torque is directly proportional to I. Now the second type is the gravity control. In this case, as the name suggests, a small adjustable weight is attached to the spindle of the moving system such that the deflecting torque produced by the instrument has to act against the action of gravity. Thus, a controlling torque is obtained. This weight is called the control weight. As you can see in this picture, there is a pointer which is moving a theta degree from the mean position, that is the spindle, and a small balance weight known as the controlling weight is attached. Controlling weight is attached in the below. Another adjustable weight is also attached in the moving system for zero adjustment and balancing purpose. This is known as the balance weight. As you can see in this picture, this is the balance weight and here is the controlling weight. Now the third type of torque is the damping torque. We have already seen that the moving system of the instrument will tend to move under the action of deflecting torque, but on account of control torque, it will occupy a position of rest when the two torques are equal and opposite. Suppose both the torques seems to be equal and opposite, then at that case it will occupy a position of rest, and this is not valid for us. However, due to inertia of the moving system, the pointer will not come to rest immediately but oscillate about its final deflection. Means the pointer will go from one point to another, but due to inertia it may not come to the original position as much as quickly as possible. So to overcome this difficulty, a damping torque is used, or you can say it is developed by using a damping device to the moving system, so that when the current flows there is a deflection and the deflecting torque moves the pointer to its final position, and due to this damping torque, the restoring force, it comes to the original position. Here you can see the picture as a damping torque. In this case, the damping torque is proportional to the speed of rotation of the moving system. In this case, we are using a damping disc that acts in between the two poles of the magnet, and the speed of the rotation of the moving system is proportional to the damping torque. This picture generally describes the eddy current damping. Depending upon the degree of damping introduced in the moving system, the instrument may have one of the following conditions, like it can be underdamped, it can be overdamped, or it can be critically damped. The case of underdamped is when the response is oscillatory, means the pointer moves from the left to right or from its main position to the maximum position in an oscillatory motion. That is known as underdamped condition. Overdamped condition, the response is sluggish, it rises very slowly from its zero position to final position. And in case of critically damped position, when the response settles quickly without any oscillation, the system is said to be critically damped. These are the basic conditions for underdamped, overdamped and critically damped. Most of the cases, critically damped is used because it is better for our instruments. The damping torque is produced by any of the following methods, means we can produce it by any of these four methods. It can be either by air friction damping, fluid friction damping, eddy current damping, or by electromagnetic damping. These are the four methods to produce the damping torque. Now we'll talk about the ammeters and voltmeters. As you know, ammeters are connected in series to measure the amount of current in the circuit flowing through the circuit, and voltmeters are connected in parallel to get the potential difference between the 2 points. Here we will study about the types of ammeters and voltmeters that we generally use in our laboratories. It can be of moving iron type meters. The main advantage of moving iron type meters are they can be used for both AC and DC applications. So they are of attraction type and repulsion type. Next is the moving coil type meters. Moving coil type meters are only used for AC and DC, but most of the time it is mainly used for DC. It is of two types, permanent magnet type or dynamometer type. Next one is a hot wire type. It is also used for both AC and DC. And the fourth one is a very popular one, that is the induction type. It is also for AC and DC. It can be of two types, that is a split phase or shaded pole type. Now let us talk about the first one, that is the moving iron instrument. An attraction type of moving iron is shown when current flows in the solenoid. A pivoted soft iron disc is attracted towards the solenoid. When this soft iron is attracted towards the solenoid, there is a movement that causes the pointer to move from its original position to a given position, and we can measure the amount of either current or voltage through the pointer. This is a type of attraction type. And similarly, just the opposite, in case of repulsion type, the moving iron instrument, two pieces of iron are placed inside the solenoid. One is fixed and the other is attached to the spindle. In this case, there is a repulsion between the fixed iron and the another which is attached to the spindle, and this gives the pointer a given position, and hence we can get a measured value of current or voltage. These two figures shown you. The first one is the attraction type. As you can see, this is the scale and this belongs to the pointer. This is the solenoidal part, soft iron disc. Whenever the current flows through this, it attracts, and in this case the pointer moves from the original position to a certain position on the scale, and this scale gives us the measurement. Here air piston damping is used, or we can say that air friction damping. Second type is the repulsion type. In this case also a scale is used along with the pointer. In this case, two types of iron pieces are used. One iron piece is kept at a fixed position and another is attached to the spindle. Whenever current is induced in the second iron piece, that is what we call the movable iron piece, it repels, and as it repels, the pointer moves some part on the scale and we get the measurement. Next type is the moving coil type. These are also two types, that is the PMMC or permanent magnet moving coil, which can be used for direct current voltage measurement. It is better used for DC sources. The dynamometer type, which can be used in either DC or alternating voltmeter. Now this is the first type of moving coil type, that is the PMMC, permanent magnet moving coil. In this case you can find two ball magnets, north pole and south pole, are fixed, and a spindle, that is the pointer, is kept at the middle, and this is the moving coil. The general principle of this PMC is based upon the principle of current carrying conductor. Whenever a current carrying conductor is placed in a magnetic field, it is acted upon a force, and this force tends to move it, and this force is generally responsible for the movement of this pointer, and we get the measurement. These are very simple things. If you are conceptually clear about electromagnetism, the type of induction, how induction occurs, how this induction gives a force, then these things will be very clear to you. These are just the application part of those things. Next type is the dynamometer type. This type is suitable for the measurement of DC along with the AC voltage and power. The deflecting torque in dynamometer relies by the interaction of magnetic field produced by the pair of fixed air core and a third core capable of angular movements. This picture shows a coil which is linked with another coil, and there is a spindle. This pointer moves on the scale. Here, this is the analysis part. Two fixed coils are kept and one moving coil is kept fixed with the pointer. Whenever there is an induction or some magnetic field is induced, it experiences a force. Whenever this experiences a force, it moves on the scale and we get an accurate measurement. This is just a pictorial view, or you can better say it as an analysis part. How the current moves into the coil. In the first part, it is moving from this to this, as you can see the arrow mark, and it comes out from here. In this case, we get the first phase. Similarly, in this case, the current reverses and moves some opposite direction. In this case, we get the phases like this. So this is the basic operation of dynamometer type. Next is the hot wire. This is not so widely used, but it has nice observation. It is based on the heating effect, as the name suggests. Consists of platinum and iridium. It can withstand the oxidation in high temperature also. Therefore, platinum iridium is used. When current is through the wire, it expands according to the I square formula. I square is the power. As power increases, as current increases, the power increases, and when the power increases, it expands. This produces sag in the wire, and the pointer is attached to the wire, shows a deflection. The last most important is the induction type instrument. These instruments are suitable for AC measurements only. This is the main, you can say, disadvantage, or a better advantage, because this is the most accurate for AC measurements, and the disadvantage is it cannot be used for DC measurement. So in this case, the deflecting torque is produced by the eddy current induced in the aluminum or the copper disc, as shown before, and this create flux created by the electromagnet. The main advantage of this is a full scale deflection can be obtained, giving long and long open scale. This is a very important advantage of induction type instrument. The effect of stray magnetic field is very small, so it doesn't give so much error. Also, damping is easier and effective. These instruments have got some serious disadvantages also. Greater the deflection causes, more stress in the control springs. Variation in supply and temperature may cause serious error unless compensating device is used. So in this case, compensating devices are to be used, and it is very important to avoid this disadvantage. These instruments are costlier and consume more power. Such instruments are mostly used in wattmeters or energy meters. This is a diagram of induction type instrument. It has a series coil, pressure coil, copper shadings used, moving disc. This type wattmeter consists of two laminated electromagnets known as the shunt electromagnet and the series electromagnet, that is the parallel or the series. Shunt magnet is excited by the current proportional to the voltage and is known as through the pressure coil, and series magnet is excited by the load current. A thin disc of copper aluminum is used as the center. It is placed between the shunt and the series magnets so that it cuts the flux from both the magnets. The deflection torque is produced by the interaction of eddy current. This eddy current is responsible for the deflection torque in the disc and the inducing flux in order to cause the resultant flux. One or more copper rings are used, and the copper shading are provided on one limb at the shunt magnet. Correct disappointment between the shunt and the series magnet fluxes may be attained by adjusting the poles to the position of the copper bands. So this was all about the measuring instruments, dynamometer, induction type, which is used in our daily life.